I am Dr. Pavitra Bharadwaj. I am Associate Professor in the Department of Computer Science in Jesus and Mary College, University of Delhi. So friends, in the last lecture, we were talking about, how the classification algorithms work, and we had seen that the technique of decision tree classifiers. So when we were using decision tree classifier, the main important step which comes in is that how to, test the particular attribute for a condition, that is how to split the values of a particular node so that you get the class labels. And we were seeing that when you have nominal attributes in your data set and you have to find out, or you have to split the values according to the nominal attributes value, the outcome has to be determined. So there can be two ways, right? So for example, if it is a binary attribute where it has got only two values, so then there will be only two outcomes. But if your attribute is a nominal attribute, like say the marital status attribute, which has got three distinct values, okay, so here now the test condition will produce three different splits. It will give three different outcomes, right? So how do we create a binary split for partitioning of all the values which are taken up by the nominal attribute into two groups? So what we will do now, our data set or our nominal attribute has got three values, but we will be actually using a binary split for partitioning these three values also, right? So how are we going to do this? We need to see this, but before this we understand that the decision trees which are used in correlation and regression trees, right, they produce only binary splits, okay. So even if you have got n number of outcomes to the test condition, the split will be a binary split. And how the binary split is calculated? It is calculated by considering all the 2 raised to the power k minus 1 ways of creating a binary partition of k attribute values. So if your attribute has got 4 values, then you will actually create the values which will be around 7 different values, 7 different binary splits can be done, okay. So how we are going to do it for a two-way split? We need to see. So if this is our values, okay, so we have the nominal attribute which is say marital status. Now this can have a multi-way split, that is the simplest, that it is giving us 3 outcomes. But if we want to make it into a binary split, then how we can do it? We can have it in 3 different ways, right, because there are 3 different outcomes. So there can be 3 different ways in which the binary split can be done. So first way is where you say marital status and you put married and single divorced in one class or in one outcome. In the other you put single in one class and married and divorced in the second. And the third can be you put single and married in one class and divorce can be your third outcome. So likewise, we can create binary splits even for multi-valued or for nominal attributes very easily. Okay. Now the next is the ordinal attributes. Now ordinal attributes, we remember we had discussed, ordinal attributes are those in which the order needs to be preserved, right. So order needs to be maintained, right. So now they can also produce binary as well as multi-way split. So ordinal attributes values can be grouped as long as the grouping does not violate the order property of the attribute, because in ordinal attributes order is important. So the grouping that you are creating also needs to keep the order in place. The order cannot be violated, right. So various ways of splitting the training records based on shirt size can be done, right. For example, if we look at this particular case where we have got the attribute shirt size. Now shirt size is an ordinal attribute because there are multiple sizes, multiple values in which the order is important. So you have small, medium, large and extra large. So you can create these 4 values are there for your ordinal attribute shirt size. Now if we are trying to create a two-way split, okay, for the shirt size attribute, only a binary split. So what we can do is we can create two outcomes, one will be small medium, the other will be large extra large. So in this the order is being preserved, okay. So the first option is correct. In the second option we put small as 1 and we put medium, large and extra large in the second outcome. So that is okay. In the third, actually if you see, we have small, large and medium and extra large. So here in the third case the order is not being preserved, right. So we need to see that when a binary split for an ordinal attribute is being carried out, the order also of the values needs to be preserved, otherwise this is not a acceptable way of splitting or grouping the ordinal attribute values. Now the next type of attributes are the continuous attributes, like for example we had seen amount of tax paid or say salary, right. So these are continuous attributes and here we have the attribute test condition, okay. So we have to represent the attribute test condition in the form of a comparison test, right, because these are generally values. So you will compare the values for producing a binary split. That is, if a particular value is less than a particular value, then you will put it in one class. If it is more than that value, you will put it in the other class, right. So we have, say for example, if we have values from I to k, so we will compare the value of the attribute value vi, okay, and the next attribute value vi plus 1, okay. So this way we will produce a multi-way split. Now again in continuous attributes also we can have multi-way split as well as binary split. So for binary split it is rather simpler. What we will do is we will find out the value which is between the minimum and the maximum value of the attribute, right. So for example, if you have a value between 1 and 100, so your minimum is 1, your maximum is 100, so you will have a medium value, say you will have 50, okay. So that value will be used for splitting the data into two binary classes, okay. So however, it is sufficient to only consider distinct attribute values in the training sets, okay, because we are looking at for split position. In multi-way split, there can be a possibility where collection of attribute value range we are using, okay. So they will be mutually exclusive and they will cover the entire range of attribute values between the minimum and the maximum observed in the training set, right. So in case of binary split, the split is much cleaner, but when we are looking at a multi-way split of continuous attribute, there we need to see that the classes that we are creating or the value ranges we are creating should be mutually exclusive. So how do we construct a multi-way split? Another way could be discretization, that is you divide it into discrete values, okay. So a new ordinal value can be assigned to each discretized value and the attribute test condition will be defined using this newly constructed ordinal attribute. So what we are doing, we are instead of having the range, we are looking at discrete values and we are ordering those discrete value. The discrete value we are giving is actually a new attribute we are creating, which is an ordinal attribute. So we can see here that if you have the test condition for continuous attributes, so if your annual income is, say, the attribute which we are looking at is annual income. So now the annual income, if you want to do a binary split, we can have a medium value. Say in this case the medium value would have been 80,000, right. So we say whether the annual income is less than 80,000 or whether it is more than 80,000. So there are two outcomes only, greater than 80,000 may yes or it can be no. So either of these two is possible, so it is a binary split. But if you want to have a multi-split in case of continuous attribute, that is also possible. Here then you will have to define two outer values, okay. So these are actually mutually exclusive values which you are trying to define. So you have less than 10,000 and you have more than 80,000 are the two outer values, and in between you will have 10 to 25, 25 to 50 and 50 to 80. So here you can see that there is some kind of overlap between the values. So a particular value can fall into any of the two classes, because say for example if the annual income is 25,000, so then it can come in two classes at the same time. So here it is not mutually exclusive, whereas when you are doing a binary split of the test condition, there the values are absolutely mutually exclusive values that you are getting. So now what are the measures which we are using for selecting an attribute test condition, because we are seeing that the entire concept of building a decision tree is depending on testing of the attribute. Right. So how do we determine or how do we select an attribute, and how do we check for the condition for the testing condition? So there can be many measures which can be used to determine the goodness of an attribute test condition, that is whether the condition which we are using is the best condition for that attribute or not. So we will give preference to the test condition which will partition the training instances into purer subsets in the child nodes, right. So pure subsets means that the class label will be the same for most of the child nodes. So if the good condition means, or the best condition for the test condition what we are defining for the attribute should find out purer subsets in the child nodes. Now purer subsets in the child nodes will be useful, because when you are when there is a node that has all of its training instances from the same class node, so it will not need to be expanded further, okay. Whereas if it is an impure node which contains training instances from multiple classes, okay, then it will require to have several levels of node expansion. And as we discussed earlier, that when you have several levels of node expansion, then the depth of your tree will become higher, it will increase considerably, and the tree which is very, very deep is not a desirable tree. So larger trees, they are not desirable because they are susceptible to model overfitting. Okay, because of model overfitting, we will see that there will be performance degradation, there will be some repercussions on the performance of the tree, right. So therefore these are also difficult to interpret, and incur the training and test time will be much higher in case of larger trees. So what we want is, we don't want the tree to be expanding too much, okay, and therefore we will want the nodes, when we are selecting for the attribute for a test condition, we will want that it should give purer nodes at the earliest. Purer nodes means the nodes for which the class label comes to be the same for all the test data. So what we will do is, we will need to check the impurity measure for a single node. That is how you need to check what is the impurity, that is how dissimilar the class labels are for the data instances belonging to a common node. So if they are coming in a common node, say for example if we had taken the example of say gives birth in case of mammals, right. So how dissimilar are they, right, whether whether most of them are saying yes or most of them are saying no, so that means it's a pure node. But if it is a lot of dissimilarities there in the class label, some are yes, some are no, so this means that your single node is more impure. So there are three measures which will be used to evaluate the impurity of the node. Okay, so if we have a node T and we need to see that how many class labels in that particular node for data instances are different, we can check the entropy, we can check the GINI index, and we can check the classification error. So the formulas are given here. We do not go into the details of how these formulas are derived as a part, that is not in the scope of this particular course here. So all these three measures, whether it is the error or it is the GINI index, all these three measures, they give a zero impurity value if a node contains instances from a single class. okay, and it will give the maximum impurity if the node has equal proportion of instances from multiple classes. So, pure node means that all the instances which are given are belonging to the same class. Impure node means that all the instances which are given, they are coming from multiple classes, or equal proportion of multiple classes. So, if you are giving say 100 test instances, so you have 4 outcomes, so 25 instances belong to each of the class. So, this means that that particular node is a highly impure node. Our objective is to create a node which is the maximum purity, right, so that we will not have to go further down and create more nodes recursively, right. Now, how to identify the best attribute test condition, right. So, we know that what is the best condition. We know that the 3 parameters are given, and the value of 0 for the 3 parameters will say that it is the best test condition. Now, to determine the goodness of an attribute test condition, we need to compare the degree of impurity of the parent node, that is before splitting, with the weighted degree of impurity of the child nodes, that is after splitting, right. So, if the impurity of the parent node is much higher than the impurity of the child nodes which are created after splitting, this means that the difference will be large. So, the better the condition will be for the one for which the difference is the largest difference. Why? Because we are moving from a highly impure node to a very high pure node. Okay, so parent node's impurity is before splitting, and after you split a particular node, you get the child nodes, you calculate their impurity. So, this difference what you see, which is also called as delta, it is termed as the gain in purity of an attribute test condition. So, delta means it is the difference in the impurity of the parent node and the impurity of the child node. Okay. So, this delta value should be the maximum. Okay. If it is the correct condition, the best condition, the value of delta will be the highest. Now, this delta value or the gain in purity will always be non-negative. It will always be non-negative because the impurity of the parent will always be greater than or at least equal to the impurity of the child. Otherwise, what is the point in splitting the parent? So, higher the gain, the purer are the classes in the child nodes relative to the parent. Now, the splitting condition in the decision tree learning algorithm will select the attribute test condition which will show the maximum gain. So, the algorithm's work is to find out that which is the condition, which is the test condition that is giving the maximum gain, which is giving the maximum gain, or which is giving the maximum value for this difference of impurity between the parent and the child, that is the delta that we just saw. So, whichever condition gives the maximum gain, that test condition will be used as a splitting criteria in the decision tree learning model. Okay. So, maximizing the gain at a given node is also equivalent to minimizing the weighted impurity measure of its children, right. Why? Because we are saying that impurity of the parent is the same for all candidate attribute test condition, right. So, what we have to do is we need to see that when we are using entropy as an impurity measure, then the difference in entropy is commonly, which is shown as information gain, that is how much information you are gaining by virtue of splitting the node. So, that is known as delta info. Okay. So, by this by using this condition, by using this measure of impurity or by using this measure of information gain, we will get to know the best possible condition, the best test condition for a particular attribute that will be used for creating the next particular level of splitting. So, when we talk about the problems that we see in case of decision tree, there is a very important aspect that we need to see, that is known as model overfitting and model underfitting also. right. So these two are the challenges, you know, which we need to overcome when we are actually building a classification model using the decision tree approach. Now for example, if we look at this two-dimensional data set, okay, now this has got instances which belong to two separate classes. So we say that the two classes, one class is represented as plus and the other class is represented as O, okay, and each of the classes has got 5400 instances. So both you know, there are 5400 instances of class plus and 5400 instances of class O. Now what we see here is a two-dimensional graph which we have plotted here. Now all instances which belong to the class O, they are generated using a uniform distribution, and the instances of the class plus, we generated them using Gaussian method. So actually 5000 instances are generated using the Gaussian distribution, which is centered at 10 coordinates with unit variance, okay, and the remaining 400 are sampled from the same uniform distribution as the O class. So O class is using a uniform distribution and plus class is using a Gaussian distribution. Mostly, like out of 5400, 5000 are using Gaussian and the rest of the 400 are taken from the sampled from the instances of the O class only. Now the first class plus class is largely distinguished from the O class. How? Because if you draw a circle of, you know, which is centered at the point 10 10, at the 10 10 coordinate, right. So to learn a classifier using this two-dimensional data set, we need to, you know, sample 10% of the data for training and use the remaining 90% for testing. Okay, so the training data set will look quite representative of the overall data in this case, right. Although we are only using 10% for training, but still, you know, because the class has been defined, like, you know, the data instances have been defined in such a way that it will be very, very representative. So if we look at this diagram, this shows the effect of, you know, varying the tree size. Tree size means the number of leaf nodes on training and test errors. So how, you know, when we increase the number of instances, how the rate of error it falls, okay, how the, you know, the data or the results of the classification tree, they become, the decision tree, they become more and more accurate. So if you change in the training and test error rates, as the size of the tree varies from 1 to 8, okay. So initially we have only one node in the tree and we gradually move to 8 nodes. So both the error rates are initially large, okay, because the tree has only 1 or 2 leaf nodes. This situation is known as model underfitting. Underfitting means that your tree has got very few leaf nodes, okay. So underfitting will occur when the learned decision tree is very, very simple, okay, and is not capable of representing the relationship between attributes and the class labels completely. This means that actually the tree which you are building is a very simple tree and it is not completely classifying the scenario. But as we increase the tree size from 1 to 8, we observe there are two things which are happening, that the error rate decreases since larger trees are able to represent more complex decision boundaries. So if, you know, our tree size comes, the number of leaf nodes is further increased, right. Even if you further increase up to say 150, then also the training error will continuously steadily decrease and ultimately, you know, it will reach a point of 0, right. So in this case where your test error rate, it ceases to decrease any further beyond a certain tree size and then it begins to increase, okay. So here what is happening, the training error rate is underestimating the test error rate, okay. So once the tree becomes too large, this difference becomes a lot. So the gap between the training and the test error keeps on widening as we increase the size of the tree, right. So this behavior actually may look counterintuitive, but it can be attributed to the phenomena of model overfitting, right. So, this we discussed about, you know, what are the condition and how the attribute can be selected, and what are the different ways, you know, in which the test error and the training error can be reduced. So, that will be all in this lecture. We will be continuing in the next lecture. Till then, please keep watching CEC. Thank you.